Hello, this is lecture number 1 for Math 609. We will start the material with the following. We will discuss at first how to solve algebraic linear systems of equations, AX is equal to B, where X is an unknown vector, A is the matrix of coefficients associated to this system, and B is the right-hand side. We start with this problem because, as we will see further, we will have different problems whose solution will end up with the need to solve a linear system of equations. And in general, a lot of problems from real life are problems that in order to solve these problems, we end up solving certain algebraic linear system. And so algebraic linear systems are fundamental problems in many scientific and engineering applications. In general, when we have a problem at hand, we need to answer several questions about this problem. The first question is, does our problem have a solution? So in our particular case, we need to answer the question whether the linear system that we would like to develop numerical methods for have a solution. If the linear system has a solution, is it unique, or we have a family of solutions, and therefore maybe we need to characterize this family. In the case that the linear system has a unique solution, we have to answer the question, how can we solve this system via a computer in case the dimension of the unknown vector is very large? Because what happens in applications is that the problem that one needs to solve culminates into the need to solve a linear system for a very large unknown vector, for an unknown vector that is in a very high dimension. The next question is, what are the available algorithms for solving linear systems? How do we implement those algorithms? How do we choose a particular algorithm for our problem at hand? How expensive is a particular algorithm in terms of how many floating point operations do we need to do in order to solve a problem of dimension n, that is that means for an unknown vector that has n coordinates. How stable is our method? So if we make a little error in the data that we have, or if the right hand side, which will be given to us, is inaccurate, how does this error propagate when we try to solve the system? Or even if we have a method that is exact in the sense that it theoretically will give you the exact solution, when we try to implement this method on a computer and design or write a program for it, when the computer does the corresponding arithmetic operations, there will be inevitably a round-off error, and this round-off error will propagate through the computation. And then the question is the method that we're using going to be stable, and whether the method will propagate that error, and whether we will actually end up with a solution to our problem that is close to the solution that we're after, or we will end up with something that would not make sense. Also, sometimes the matrices that we have, the matrix that is associated to the linear system, has a special structure, And certain numerical methods are faster or are designed for matrices with a specific structure, and we need to know this method. We need to make use of the special structure of the matrix A, and therefore design a method that would utilize that structure and will perform better because of this inherited structure of the matrix A. But before going into details, I will just talk about the notation and certain facts that we need to know from linear algebra in order to continue further. We will discuss vectors X, which are column vectors, and are written in this form with n coordinates. Those coordinates can be either real numbers, and then we will denote that by writing X belongs to Rn, or these vectors are with complex coordinates, and we will denote this by writing X belongs to Cn. Sometimes we will write the vector as a vector row, and then we'll write T, which means the transpose of that vector. The matrices that we're going to deal with will be mainly matrices with real entries. And here A is written as a matrix of dimension m times n, which means m rows and n columns. The matrix can have also complex entries, and we will then denote this as writing A belongs to C m cross n. But in our algorithms, we will mainly deal with square matrices in which the number of the rows is equal to the number of columns. And as you all know from linear algebra, this is how a matrix is written. This is a matrix with m rows and n columns, where the generic element is aij, where the index I shows us the number of row where this element resides, and j tells us the number of column where this element resides. Examples of simple matrices that we're going to use. First, with I, we will denote the identity matrix, which is a square matrix. In our consideration, this will be a matrix of dimension m times m. This is a matrix where we have ones on the main diagonal and zeros everywhere else. We will discuss also upper triangular matrices. We will denote them by U, and those are matrices for which all the entries of these matrices below the main diagonal are 0, but the entries above the main diagonal or on the main diagonal may or may not be 0. Similarly, lower triangular matrices will be matrices for which everything above the main diagonal will be 0. And the elements on the main diagonal and below the main diagonal, which here they are denoted by Lij, with the obvious restrictions for the indices I and j, they may or may not be equal to 0. We will then continue with some definitions. A square matrix is called symmetric matrix if it has real entries, and it is such that the transpose matrix of this matrix coincides with the matrix itself, or basically this is a matrix for which the element Aij is equal to the element Aji. A matrix is called the Hermitian matrix if it has complex entries, if it is a square matrix and it conjugate transpose coincides with the matrix A. So by A star, we denote the conjugate transpose of the matrix. This is a matrix whose components are AJI complex conjugation. What is complex conjugation? So if I have complex number A plus IB, and I would like to look at its complex conjugate, which I denote by bar on the top. This is the complex number A minus IB. So what is changed? Just this sign here from plus goes into minus. And a matrix that satisfies this condition is called a Hermitian matrix. And if we have a Hermitian matrix, if we put here in this general equation, if we consider the case when I is equal to J, then we will have that AII is equal to AII bar, which means that on the main diagonal, the entries on the main diagonal coincide with their complex conjugates. And this is possible only if the entries are real. So if we have a Hermitian matrix, on the main diagonal, we have real numbers, and of the main diagonal, this element corresponds to this element. And the only difference is that in front of the imaginary part here we have plus, and here we have minus, and the same thing here. This element corresponds to this element, and the only difference between those will be that in front of the imaginary part you have in one place minus, and at the other place plus. Similarly, a matrix that is square matrix and has complex entries is called a skew Hermitian if the complex conjugate of the conjugate transpose of this matrix coincides with the negative of the matrix. Then I will remind you what is how we define a product between two matrices, A and C. In this particular case, if the matrix A is of dimension L times M, and the matrix C is of dimension M times N, so the number of the columns of the matrix A has to coincide with has to be equal to the number of rows of the matrix C. Then we can talk about the product of these two matrices, and the corresponding ijth term of the product matrix B, which is Bij, is given by this sum. In fact, what do? We take the ith row of the matrix A, and we multiply it scalarly by the jth column of the matrix C. So if we have, for example, here 3 components, here we have to have 3 components, then we multiply this number by this number, and to the product we add this number by this number, and to the product we add this number by this number. Another useful way to view matrix multiplication is the following. If we look at the matrix B and we denote by B1, B2, and so on, the matrix will be of dimension L times N, so Bn, if those are the columns of the matrix B. Then the jth column of the matrix B, which is the product of the matrices A and C, is basically a linear combination of all the columns of the matrix A, where the numbers in this linear combination are the components of the jth column of the matrix C. So if this is the matrix C, this is the jth column of the matrix C, and those are the components of the jth column of the matrix C. Those numbers here are used as linear combination in front of the columns of the matrix A. So here is the matrix A, and it has columns A1, A2, and so on, AM. And this is the jth column of the matrix C. So this number multiplied by this column, this number multiplied by this column, and so on, this number multiplied by this column will give us the jth column of the matrix B. What is the range of a matrix? The range of a matrix is the set of all y such that y is equal to ax for some vector x in Rn, provided that we consider a matrix with real entries. So what does that mean? When the vector x marches within Rn, then we look at the image ax, and then the set of all these vectors is called a range of A. And because of this description of multiplication of a matrix by a vector that I described, we can think of the range of A, which is a useful way to view it. It is basically the range of A is the space that is spanned by the columns of the matrix A. So if I have the matrix A and I look at its columns A1, A2, and so on, A, in this particular case, the number of the columns will be N. And then AX then would mean what? AX will be the matrix A multiplied by the vector X will be X1 A1 plus X2 A2, where X's here are numbers and A's are the vectors and so on, plus X n times AN, where ANs are vectors in the dimension Rm. And so the range of a matrix can be viewed as the space spanned by the columns of the matrix. A column rank of the matrix is the dimension of the space spanned by the columns of A, and rank of A, it is the dimension of the range of A, which is the same as saying that this is the dimension of the linear space spanned by the columns of the matrix A. A matrix of dimension m times n is is said to be a full rank if it has the maximum possible rank, and the maximum possible rank is the minimum between the number of rows and the number of columns. The null space of A is the set of all vectors that the matrix A sends to 0. So these are the set of all x's in Rn such that A times x is equal to 0. The transpose matrix of the matrix A is the matrix, we already used the symbol transpose to when we define the symmetric matrix. This is a matrix. So if the original matrix was of dimension m times n, A transpose will be a matrix of dimension n times m, and this is a matrix for which the columns of the matrix A become rows of that matrix. And if you have the product of A B transpose, then this is the B transpose times A transpose, which is the main equation that relates to the property to transpose a matrix. And the conjugate transpose, if A is a matrix of dimension m times n with complex numbers, complex entries, then A star is also a matrix with complex entries, but now it will have n rows and m columns. And the elements of this matrix, the ijth element of the matrix A star is equal to the jith element of the matrix I at the matrix I complex conjugate. And again, the same rule as for the operation here, that AB star is equal to B star times A star. As I mentioned in this class, we will be interested predominantly in square matrices, whether of dimension n or square matrices of dimension m, where their entries will be mainly real numbers. A matrix is called invertible matrix if there is a matrix which we denote by A inverse, such that A times A inverse is equal to A inverse times A is equal to the identity. And this matrix is called the inverse of the matrix A. And the basic property of taking an inverses of a product. So if we have two matrices of the same dimension n, and we multiply them, the inverse is this product, the product of the matrix A inverse times the matrix B inverse. Let me remind you that matrix multiplication is not commutative, so one has to be careful about the order in which one writes the matrices when they are multiplied by each other. For every square matrix, to every square matrix, we associate several numbers. One of the numbers that we associate to a square matrix is called the determinant of this square matrix. And there are various ways in which one can compute a determinant of a square matrix. In general, the formulas involve quite a lot of computations, and among the formulas that are known for determinant, I had chosen to write down this one, which is called the Laplace expansion along the ith row. And this is a recursive formula that computes the determinant of an n times n matrix via n determinants of n minus 1 times n minus 1 matrices. Easy way to compute determinant is only can be done only for matrices of dimension 2 by 2 and 3 by 3. So in case when you have a 2 by 2 matrix, a determinant of a 2 by 2 matrix is the product of the elements on the main diagonal minus the product of the elements of the main diagonal. And also there is a sort of neat rule to compute the determinants of a 3 by 3 matrices. But if you go to dimension higher than that, then this is quite a computationally intense procedure. However, if one knows the eigenvalues of a matrix, then the determinant of this matrix can be computed easily by just multiplying the eigenvalues of the matrix. Or if the matrix has a special structure, then determinants are easily computed. The determinant of the identity matrix is 1. The determinant of the lower triangular matrix, and here should be U. And the upper triangular matrix that we just defined are easily computed because they're just the product of the elements on the main diagonal. So if we have a lower triangular matrix, the determinant of this matrix is the product of these elements on the main diagonal. And if you have an upper triangular matrix, the determinant of an upper triangular matrix is just the product of the elements on the main diagonal. Another set of numbers that we associate with a matrix are the so-called eigenvalues of a matrix. If we have a square matrix of dimension n times n, then we associate with it n complex numbers, and where n is the dimension of the matrix, and these are the eigenvalues of this matrix. An eigenvalue of a square matrix is a complex number. And it is, we say that lambda is an eigenvalue of the matrix A with corresponding eigenvector V, which is non-zero. If when we apply the matrix A to the vector Z, we end up with multiple of the vector V, and this multiple is exactly lambda times V. So this relation here can be written, which I wrote further, can be written in the following way. We move this term on the left, and then we have AV minus lambda, and here we insert identity matrix times V is equal to 0. Anything multiplied by the identity is the same thing, so whether we write down the identity matrix or no or not doesn't matter, but it is then easier to pull out V to the right, and then we will have A minus lambda I. This matrix applied to the vector V is equal to 0. And since an important fact in the definition is that the vector V is a non-zero vector, and therefore we end up with the fact that we have a system of n equations with n unknowns, in this particular case, the vector V, that has a 0 right-hand side, but has a non-zero solution. And according to theorems from linear algebra, this is possible only when the determinant of the matrix associated with this system is 0, and therefore we have that the determinant of A minus lambda I should be equal to 0. Now, if one looks at the particular form of this matrix, this is the matrix A11, A12, A1n. Those are the entries of the original matrix A, A22, A2n, and so on. We have AN1, AN2, and then ANn. And from this matrix, we subtract lambda times the identity matrix, which is the matrix that has lambdas on the main diagonal and zeros everywhere. When we subtract two matrices, we subtract all the entries of the matrices, and therefore the matrix A minus lambda I will be this matrix, and we want the determinant of this matrix to be equal to 0. However, if we use the rules, even for example, this rule that I wrote here, the Laplace expansion, to compute this determinant, one finds out that this, in fact, if you write it down, you will end up with a polynomial of degree n, which is called a characteristic polynomial, corresponding to the matrix A with respect to lambda. And therefore, this equation here, called also the characteristic equation, will be an equation that is looking for the roots of a polynomial of degree n. And according to main theorem of algebra, every polynomial of degree n has exactly n roots, which are in general complex numbers. For example, we can illustrate that if we have the polynomial lambda minus 1 squared is equal to 0, which is a quadratic function, and it has two roots, 1 and 1, with so it has the root 1 with multiplicity 2, or we can have lambda minus 1 times lambda minus 2, for example, is equal to 0. This will have the two roots 1 and 2, or we can have something that if you have a quadratic polynomial, then the roots will be complex conjugate numbers, always a root that will be a plus ib, a plus ib, and a minus ib. So this is another list of all possible possible roots in the case when n is equal to 2. But in general, you can have n roots, and some of them may have higher multiplicities and some of them may not. But if you write them as many times as their multiplicities and write them down, each of them, then you will end up with a list of n numbers. Now, we, in our investigation, will further, we will make use of this theorem, which somehow encapsulates more or less all the information and the notation and terminology that we discussed so far. So if we have a square matrix with complex entries, it is true also for a matrix with real entries. then the following conditions are equivalent. So A is invertible if and only if the rank of the matrix A is n, if and only if the range of the matrix A is Rn, if A is with real entries, and Cn if A is with complex entries. If and only if the null space of A consists only of the zeroth vector, if and only if the determinant of the matrix A is non-zero, if and only if zero, the number zero, the scalar zero is not an eigenvalue of A, and if and only if the columns of A are linearly independent. Okay, so this part up to here was sort of recollection of what we need to know from linear algebra in order to continue further. Of course, once we go more into detail, if we need some more terminology, then we will introduce it as we go. And now if we look at the problem that we are going to discuss, we have a matrix with complex or real entries that is a square that has n rows and n columns, and that is invertible. And we would like to find the vector x such that ax is equal to b. In this particular case, as we discussed, if we look at the matrix A and we look at the columns of the matrix A, A1, A2, and so on, AN, and we look at A times X, so A times X then will be the number X1 multiplied by the first column plus the number X2 multiplied by the second column, and so on, plus the number xn multiplied by the last column. And we want this to be equal to b. Now, if we see here from our previous theorem, the determinant of A is different from 0 is equivalent to the statement that A is invertible. We know that A is invertible, therefore the determinant is different from 0. And also we know that A is invertible, and therefore the columns of A are linearly independent. So these columns A1, A2, and so on are linearly independent vectors in Rn. And what we're looking for these numbers x1, x2, and so on, xn, which are exactly the representation of the given vector b to us with respect to the basis a1, a2, and an, which is a basis for the space Cn, or if we talk about a real entry matrix in the space Rn. So given a vector b to us, given the matrix A, we know these columns A1, A2, and AN, and we are interested in finding the representation of B with respect to this basis. It is X is nothing but that numbers that are the coefficients of this representation. Of course, if we know that A is invertible, we can just say, oh, we multiply here by A inverse, and therefore on the left, and therefore A times A inverse will be X, and then we will have A times A inverse times X is X, and therefore we will have that X is equal to A inverse B. However, in practice, this is not the formula that in fact is used, because for large n's, which are problems that are coming from real life, A inverse, the computation of A inverse is very difficult, and this is not what people do for various reasons. Another way, so we cannot use this formula to compute X. Another way people may also look at this problem is that we know from the Cramer's rule that the numbers xi, which are the coordinates of the vector of the unknown vector x, have the representation delta I over delta, where delta is the determinant of the matrix A. Since A is invertible, the determinant of A will be different from 0, so this number here will be well defined. And delta I is a determinant of another matrix. What is this other matrix? This is a matrix which you look at the matrix A, and then with this index I here, we look at the ith column of the matrix A. And we remove that column from the matrix A, and we instead insert the right-hand side, which is the vector B. This way we get a new matrix. We compute the determinant of this new matrix, which will be the number delta I. And then we have a formula that the ith coordinate of the unknown vector is just the ratio of these two numbers. Again, for big N and in computation, this rule is not used for various reasons, and this rule has only a theoretical use. So in practice, in engineering applications, people are using various numerical algorithms to solve the linear system, especially for large values of n, for large dimensions. And somehow we can divide all these algorithms for numerically solving the linear system into two big groups. We can say that there are some algorithms that are universal, in the sense that we have the algorithm, and this algorithm can be applied for solving any system. AX is of the form AX is equal to B for any invertible matrix A. And so we have this recipe or this rule for any A. And if our matrix that we have in our hands has more special structure, then this rule basically gets a little bit simpler, which we're going to see here as we go along with the lecture. Or there are some methods that only work for particular matrices. For example, there are methods that are tailored to the particular structure of the matrix A. There are methods that can be used only for cases when A is symmetric or positive definite. Or there are methods that can be used for matrices that are sparse. Sparse means that these are matrices with huge dimensions, but they in some sense are simple because they have a lot of entries that are zeros. Also, if we look at the numerical methods for solving linear system, they can be classified as direct or iterative methods. These are the other two main groups. What are direct methods? These are methods that in theory give you the exact solution to the system after finite number of steps. So you have some formulas and after you perform a finite number of computational steps, then at the end, you will end up with the exact solution to your problem. However, since these methods will be implemented on a computer, every time when a computation is made, namely addition, subtraction, division, or multiplication, the computer is not going to perform the operation exactly. The computer will not use the real number that one has at hand or is the result of the corresponding computation. It will round off or it will approximate this number to a certain fixed net of numbers with which the computer operates, and therefore every time a computation is performed, there will be an error, which is called a round-off error. And it is important to keep track of this round-off errors, and it is important to see, even though the method that is theoretically sound, written on a piece of paper, how this method will be affected by this round-off errors. Another set of or category of methods are so-called iterative methods for solving linear systems. Those methods are methods that do never give you the exact solution of the system. You cannot hope for exact solution anyways, even if you have a direct method, because you have to implement it on a computer, and the computer always will give you a round of error. But in the iterative method, you will perform computations, and after each step, the method will produce some vector that will be an approximation to the exact solution to the system. And the more steps you do of this method, hopefully, if the method is convergent, then you are going to get closer and closer to the exact solution of your system. So those are called iterative methods, and we will discuss both of those methods in our class. And even though in the book they are put in a separate chapters, I will discuss them one after another. So there will be a certain reorganization of the material. Now, we will start with direct methods, and with direct methods, we will talk about forward elimination, backward substitution, and also Gauss elimination. When the matrix A has a special structure, then of course the solution of the system AX is equal to B, or finding the solution of the system AX is equal to B can be easier than if A is a general matrix. For example, if A is a lower triangular matrix, since we want the determinant of A to be different from 0, and the determinant of A, since it is a lower triangular matrix, is a product of the elements on the main diagonal, so we will require that the elements on the main diagonal are different from 0. And so once we write the system AX is equal to B, which is the same as writing LX is equal to B, and now write down that L is a lower triangular matrix, we see that the first equation, which basically is this row multiplied by the vector X, will give me L1, 1x1 is equal to B1. So the first equation will have only one unknown. This is the unknown x1. The second equation will have two unknowns. This is the unknown x1 and x2, and so on. This is the ith equation. The ith equation will have x1, x2, and so on, xi, all these unknowns, and only them. So what is happening then? That's why the method is called forward elimination, because we start from the top, we go down forward and eliminate the unknowns one by one. So from here, since L11 is different from 0, we can write exactly what x1 is. Now, since x1 is known, we use it right after we find it in the second equation, and then the second equation will have only one unknown, and this will be the unknown x2. Then this now will be known. This will go on the right hand side, and then we solve for x2. Once we solve for x2, this will be the expression for x2, and so on. When we get to the ith equation, we will have already computed x1, x2, and so on, xi minus 1, and the only unknown, that effective unknown, we will have by the time we reach the ith equation will be xi, and therefore all the terms here that are to the left of xi are known. We move them on the right hand side, and we find the expression for xi. And finally, when we go to the last mth equation of the system, everything up to that moment will be known, and the only unknown part will be xm. Then we move here this part to the right, and we find an expression for xm. Now we need to count how expensive this forward elimination method is. In your book, they count only the divisions and the multiplications because they require more resources, but in some other books they count the flops. That means they count all the floating point operations, and this is what we are going to do as well. So at step one means that we solve the first equation. We see that we have one division. This is this division. At step 2, we also have one division. This is this division. Step 3, we have one division. But step I, we have one division. Basically, at each step, we have one division. So all the divisions are 1. Then if we look at the subtraction or addition, then here we have 0 subtraction or addition. Here we have 1. Then the next step we will have 2. In this particular, at the ith step, we will have I components. When we move to this side, we will have I components here, and then the operation is done in between each 2 components. So we'll have I minus 1 subtractions. At the very end, we will have m minus 1 subtractions. So the subtractions start with 0 subtractions at step 1, 1 subtraction at step 2, and so on, m minus 1 subtractions at step m. The same with multiplications. At the first step, we don't have any multiplication. The second step, we have this multiplication. At the ith step, we'll have multiplication li1x1 up to lii minus 1xi minus 1. So at step I, we have I minus 1 multiplications. At step m, we have this multiplication and so on up to this multiplication. So from 1 to m minus 1, we end up with m minus 1 multiplications. So the total number of operations is total number of divisions plus total number of subtractions plus total number of multiplications. The divisions are ones every time, m times. So this is the number of the divisions. The subtractions and multiplications, these are twice because they're both for the subtractions and multiplications, and they are the sum of the numbers 1 plus 2 and so on plus m minus 1, which corresponds to that sum. And then, so this m goes to here, and then the sum of the first m minus 1 terms, so 1 plus 2 plus and so on plus m minus 1. There is a formula for the sum of the first m integer numbers. This is the number that you end up with, which here is m minus 1, times the number that you end up with plus 1. So m minus 1 plus 1 will give you m over 2. So that sum here is this. We multiply it by 2. 2 and 2 will cancel out, and this will give you this term. And whenever operation count is concerned, the leading one looks at the leading term. That means the term with the highest power. So the term with the highest power here will be m squared. So the operation count is approximately m squared. Sometimes they write big O of m squared, which means constant times is bounded by a constant times L squared. So let us keep in our mind that if we do forward elimination, which is a method that works only if the matrix is lower triangular matrix, then the operation count is approximately m squared. Similar thing is done when the matrix A is is an upper triangular matrix. Since the determinant is different, since A has to be invertible, because these are only the only matrices that we are discussing. The determinant of this matrix has to be different from 0. The determinant of an upper triangular matrix is the product of the elements on the main diagonal. And since the product has to be different from 0, then each term in this product has to be different from 0. And for upper triangular matrices, the method for solving a linear system is called backward substitution. And again, we write AX is equal to B. Instead of A, we write U because A is upper triangular matrix, and then write down what the system is and what the corresponding equations are. And so what we do, we start from the bottom up this time. That's why it's called backward substitution, because we start from the bottom and make all our way up. Why do we start from the bottom? Because if we look at the bottom, there is only one unknown, and this is the xm. If we go to the next to the last equation, then we will have two unknowns, x m minus 1 and xm. So basically the picture is the same as this one, but not from the top to bottom, but from the bottom to the top. And we do the same, we apply the same strategy. Since UMM is different from 0, we write xm as the here it is U as a ratio, so it is a misprint, here is U, as a ratio of BM and UMM, and then we continue to the next equation. By that moment, this will be known, and this will be the only unknown, and therefore the known part will move to the right and divide by this term, and we'll find an expression for xm minus 1. And so on, we make our way up to the last equation. At the very last equation, we will have that all these elements are known, because by the time we reach the first equation, all this will be known. We move them to the right hand side, and we will have the expression for x1. And exactly the same way, we count the operations, and we find out that the operation count is the same, that the operation count is about m squared. Now, we continue with the next method, which is Gauss elimination. Gauss elimination is a very widely used method for solving linear systems. And it is a method that probably you have studied quite intensively in linear algebra. One can view, or at least here in this class, we will view the Gauss elimination method in two ways. We will see how we can use it to solve linear systems AX is equal to B. And also we will use Gauss elimination as a vehicle to do a factorization of the matrix A, namely as a vehicle to write the matrix A as a product of two matrices, a matrix L, which is a unit lower triangular matrix. So L is a lower triangular matrix, and we add this unit lower triangular matrix because L will be a matrix for which all the diagonal elements are ones. And so A will be a product of a unit lower triangular matrix L and upper triangular matrix U. So when we do Gauss elimination, probably you remember from linear algebra, you end up with an upper triangular matrix, and this U is the upper triangular matrix that you end up with. And then you do backward substitution to actually find the solution of your system. Meanwhile, when you perform the computations in order to arrive at U, you will have some information that you can utilize, and this information can be used to construct the matrix L that participates in this factorization of the matrix A. This factorization of A is called LU factorization of the matrix A. And LU factorization for the matrix A can be achieved not through the Gauss elimination, but it can be achieved through just simply write down the system, write down the unknowns for L, the unknowns for U, which means the entries for L and the entries for U, and then perform in a clever way, perform the necessary the multiplication of those two matrices. And once you do that, you will end up with equations that will determine the entries of L and U. So the bottom line is that we are going to use the Gauss elimination to write down the LU factorization of the matrix A. That means writing A as a product of a unit lower triangular matrix and upper triangular matrix, or we will see that not every matrix A can be written in this form. If the matrix A cannot be written in this form, we will see that we can find a permutation matrix P such that not A is equal to L times U, but P times A is equal to L times U. So not A by itself is the product of L and U, but if you multiply a permutation matrix times the matrix A, which basically means that we will do some permutation of the rows of the matrix, then we'll end up with a matrix that has the LU factorization. So let's know that what is the goal with the Gauss elimination. The Gauss elimination transforms a full linear system. What do we mean by full linear system? That means that basically all entries are non-zero. So this is a full linear system. All the entries here are not zero. And so what we do is that after, so this is a 4x4 matrix. After performing the Gauss elimination, we end up with the upper triangular matrix. So we have 0 here, and everywhere below the main diagonal we have zeros, and now above the main diagonal we may or may not have zeros, but on the diagonal we are not going to have zeros. So so what is happening is that the Gauss elimination transforms this full system into an upper triangular system. And how does it do that? It does that by, as you know, you have you stay on a particular row, and then you add to this row another row of the system multiplied by a number. So this is basically a simple linear transformation, and we will see how this can be expressed in terms of matrices. So the idea is to introduce zeros below the diagonal in the columns of the matrix. So here we see the goal is to find to make everything below the main diagonal 0. And what is the execution? So if one thinks about the execution, we subtract multiples of each row from subsequent rows, if you remember from linear algebra. And this action, subtracting multiples of each row from subsequent rows, actually can be achieved by multiplying the matrix A on the left by a particular a sequence of lower triangular matrices LK. So we have the matrix A, and then let's say we have AX is equal to B. Or we can we may not associate the matrix to the system. We may think of doing an LU factorization of the matrix A without associating it to a particular system. Now, if what we want, so we start with our original matrix. Here, our original matrix has some entries, which are stars and have index 1. That means these are all the entries at the first step. Then what we do is we multiply to the left the matrix A with the matrix L1, which is a lower triangular matrix, and we will see how to find it. The matrix A by the matrix L1, and as a result, the resulting matrix, which we denote by A2. So A2 is L1 times A1. This will be the resulting matrix. After this multiplication, so A2 is equal to L1 times A. And this matrix will have zeros everywhere below the main diagonal on the first column. this row will stay the same as the original row. So the elements of this row will be the same as the elements of this row here. But these elements here now will be different because some algebraic operations are performed on those. And these elements will be different from the corresponding elements in these positions in the matrix A. Now we multiply this matrix by lower triangular matrix L2. And as a result, we will end up with the matrix. So this will be L2 times L1 times A. And as a result, so we will keep unchanged the first row. We will keep here unchanged the second row. We will have that below the second column, everything is 0. So this will be 0, which we basically will make this element 0. And then these elements here, they will change because we'll do some arithmetic operation over them. So they will be the elements that will be the elements of this matrix. And then the last step will be we multiply this matrix on the left by a lower triangular matrix L3. When we do that, we will end up with this matrix, which will be L3 times L2 times L1 times A. And at the same time, this will be the upper triangular matrix that we are looking at, because after this multiplication, we will have the first row unchanged. We will have from the previous step, we will have the second row is unchanged from the previous step. We will have this row here unchanged from the previous step. Everything below the diagonal on the third column will be equal to 0. So this will be 0. And then the only thing that will be changed then will be this term here from the previous step. So we will have that. So now let's come back. This is in the case of 4 by 4 matrix, and in general, in the case for M by M matrix, what we will end up is that we will end up multiplying the matrix A on the left by a sequence of lower triangular matrices. And as a result, we will end up with the matrix U. So now if we look at the multiplication of those matrices, this will be also a matrix of dimension M times M. And we will see that this matrix will be invertible. And if we write this matrix as L inverse, so what we will have L inverse times A is equal to U. And if we multiply both sides on the left by L, we will have that the matrix A is equal to L times the matrix U. And this is the LU factorization that we were discussing. Now, if L inverse is equal to those matrices, because we denoted by L inverse the product Lm minus 1, then we have Lm minus 2, and so on. We have L2 and L1. To find what is L, L then will be the inverse of all those matrices. So will be Lm minus 1 up to L2 times L1, and this is the inverse of all these matrices. And then using the rule for finding an inverse of a product, this will be exactly L1 inverse times L2 inverse, and so on times Lm minus 1 inverse. So what we need to do is we need to first find how the multiples, how this operation, subtracting multiples of each row from subsequent rows, can be done by multiplying the matrix A on the left by particular lower triangular matrix. So we have to determine what all those matrices are. And we have to see that they are such that when we look at their inverses and when we multiply them, we end up with a matrix that is a lower triangular matrix. And then we will have that the matrix A can be represented as a product of a lower triangular matrix that have ones on the main diagonal and an upper triangular matrix. So basically this is in a nutshell the idea of Gauss elimination, how to construct the matrices L. The matrices, the final matrix L is actually never, if we want to solve the system, is never constructed. But if we want to, never constructed explicitly, but if we want to look for the LU factorization for the matrix A, then we can and should save it every time we do the computation. So now, if we go further with the Gauss elimination and look at the details, what we have here is that let's stick to the notation that the matrix that we begin with, we associate with upper index 1. Here is lower, but here is upper index 1 of its entries. Then the matrix after the first step, we associate with an upper index 2. So we see here that after the first step of the Gauss elimination, the first row is not changed. So here, these entries will be the same as the first row of the original matrix. And then the entries that will change will be the entries of this submatrix. They will be different from the entries of this submatrix of the original A. And then all the elements below the main diagonal on the first row will be equal to 0. And in general, at the kth step, what we are going to have, the matrix AK will have the following structure. The elements will have some elements on the main diagonal up to here. Then this will be the element AKK. So this will be this element here, which is called the pivot element AKK. And then we'll have some elements below the main diagonal. So here, this is a kth row. And here, this is the kth column. So the elements on the kth row and the kth column at the kth step. Here, everything will be 0. As you can see, all the elements here will be 0. And then what we are going to change, we are going to change, so this is the element AKK, we're going to change all the elements that are below, right here, below the kth row. So all these elements here, the next step will be changed. And all these elements that are in blue at the next step will end up with 0. So how do we do that? If we look at the first step, and as I said, the element AKK is called the pivot element. So if we look at the first step, what we do, at the first step, we multiply, we want to make all these terms here 0. So we want to make this term 0 and so on. We want to make this term 0. What do? We assume that A111 is different from 0. And therefore, we can multiply in order to make this term 0. We have to multiply the first row by a number such that when we add it to this row, we will make this term 0. And what do we multiply it by? We multiply it by A211 divided by A111 with a negative sign. So if we multiply the first row by that number and add it to the second row, A11 with A111 will cancel out. Then we will have minus A21, which added to A211 will make it 0, and then we will end up with 0 here. And then this will change all the subsequent elements in this row to these elements with an index 2. This way we make the term A211 to be 0. Then what we do, we look at the first row and we want to move to make the element on row 3 the first element on row 3, 1, so it will be A3, 1, 1, and then we'll multiply it not by this number, but we'll multiply it by the number minus A1, 3, 1 divided by A1, 1. Then if we multiply the first row by that number, and we add it to the third row, then we will make the corresponding term in the third row 0, and we will change also the subsequent elements in this third row. This is what is happening after the first step. And in general, if we look at the kth step, then what is happening at the kth step? In order to continue with these steps, we see that for the first step, the element A11 has to be different from 0. Then we arrive from the matrix A1 to the matrix A2. Now we basically repeat this operation. We forget about this part of the matrix, and then we concentrate only on this matrix. If we do operations between the rows from the second to the nth, these operations will not affect the first terms of this row because they're all 0. And now we can do exactly the same. What we did for the first matrix, we can do it for this submatrix. In order to do that, the element A22, which is the second pivot element, has to be different from 0, and so on. Here, if we come to the kth step, at this step, we now forget that we had done all the job for the first k-1 rows, so we don't need to touch them anymore. That's why if you see here, they will be kept whatever they were up to that stage, and the only change will happen at row k plus 1, and so on up to row m. So all the change will happen in this submatrix. And then what we want to do, we want to make all these blue numbers here zeros. And how do we do that? We multiply the first row by the number a k plus 1 k k divided by a k k k with a sign minus. If we do that, then AKK will cancel with LKK, and then as a result, in the first term of this row here, we'll have minus AK plus 1K, which will add it to this term, will make it 0. And we will also have modified the rest of the elements in this row. If we write down the actual formulas, then the formulas are the following. First, we compute the numbers LJK, which are exactly, if you see, these are those numbers, AK plus 1 KK divided by AKK. So those numbers are all, the numbers LJK will be all the numbers that have in the denominator AKK, and in the numerator they will have AJK when J is from K plus 1 to M. So how do we remember those? So how do we get, for example, the number LK plus 1K? This number is this term divided by the corresponding pivot. So this will be AK plus 1KK divided by the pivot AKKK. Then what will be the next one? K plus 2K. Then it will be the element that stays on the K plus second row and kth column. So it will be AK plus 2KK divided again by the corresponding pivot element AKKK. And this is exactly what is written here. Is just that the index J here, it is written in terms of the index J, and J runs from K plus 1 to M because it starts from this K plus 1 here and runs up to M. So we make these numbers, and these are exactly the numbers that we will multiply the kth row. You see here, this is the number, this is exactly the number L K plus 1K. And this is the number that we will multiply the kth row. So what we do is to make the change, and we know that when we do this operation, then all the elements in this in this column here will be equal to, this part of the column will be equal to 0, and then we're gonna make change only here, and then the new elements, that the new entries of the matrix, we denote them by index k plus 1 because they will be changed. And what will they be? They will be the old entries that stay there, which are denoted by index k, so all the AJKs that stay there, and then minus, because we want the sign minus in order to make 0 these blue terms, minus the element LJK, which we know how to compute, and we know we want it because we want to make the blue element 0, times the corresponding element AK IK, so times the corresponding element that is on the ith row, where the row is here, and on the kth column. So this is this corresponding element of this pivot, I would say pivot row that stays on the ith column, because this is the element AKIK. So we have minus LK the corresponding L term multiplied by that element and added to the corresponding term that stays in this position, JIK. So this is the main algorithm, or the main rules by which we perform Gauss elimination at step k, for k from 1 to m minus 1. And they all involve here making the idea is to make all the blue terms at step k to be 0. This is the Gauss elimination. And this is can be done only if every time after every step the pivot element that shows up, which is the element here in the corner of the submatrix, the pivot element that shows up is a non-zero element. Only then we can do that, because only then we can compute the numbers L, J, K. And now the claim is that if you look carefully at what these equations give you, and then if you look carefully at the matrix LK, which I will explain how to construct, then you will see that these operations here written on these two rows actually can be done by multiplying the matrix AK on the left by the matrix LK. So how do we construct the matrix LK? If we look back here, we know that at step K, we are at row K and column K. So this is the column K. Now, what we do is we construct the matrix LK the following way. We write identity matrix everywhere. And then we look at the column K. So this is column K. The column K will hit here the identity where this is the row K. And then what we have here is row K plus 1 after the row K, and so on. We will have here row M. What do we put on row LK plus 1? We put the element LK plus 1K. Then on row K plus 2 and column K, we put LK plus 2K, and so on. And this is exactly what is written here with a negative sign. So we have the identity matrix. This is the identity matrix. This is the kth column. And this is part of the kth column that lives below the main diagonal. We populate only this kth column with the negatives of the numbers L, which are what numbers? Which are, we look at this number AK plus 1K at step K divided by the pivot, and write down the index, which is the same as the existing index K plus 1K, and so on up to the last term here. We look at this term, we divide it by the pivot element and populate the matrix at this, give it index MK and write it down as an index right here with a negative sign. So if you write down the matrix LK and you look at the LK times the matrix AK, so what will happen is if I have here the matrix AK, we know that the matrix AK has the following structure. So here is this pivot element AKKK, and here is something is happening. Here is the main diagonal, and here everything is 0. And using the rules for multiplying two matrices, once you write down carefully what this multiplication is, you will find out that this operation here is the same as multiplying the matrix AK on the left by the matrices LK. So this will be the end of the lecture. What we will do next time we will discuss properties of this matrices LK. And we also will discuss how the Gauss elimination is performed for matrices that are have some matrices that have special structure. Okay, thank you. See you next time.